Hi, today we're going to learn about one of my favorite topics, astronomy. And specifically, we're going to learn how to calculate quantities related to objects in orbit, such as satellites around the Earth, moons around planets, or even the planets around the Sun. Let's get started. To begin, I'd like you to imagine a cannon that might be on top of a mountain, and we shoot the cannonball off. At first, the cannonball just goes and falls a little bit further away, let's call that path A. But then we decide to add some more gunpowder and make it come out faster, and so we see that it travels a little further around the Earth. That might be orbit B. Well, imagine if we put so much gunpowder in that it left going so fast that as it was moving forward and falling down, the Earth curved down underneath it because it's a sphere, and it just kept going just far enough and the Earth falling just enough underneath it that it stayed at the same approximate height above the Earth. Well, if we could find this magical amount of gunpowder, then we might produce the path that is drawn there in C, where the cannonball goes all the way around and hits us in the back of the head. Now, how much time would we have to duck and get out of the way? After all, you might have seen the Bugs Bunny comic where he throws a baseball and it goes all the way around the Earth. And
Approve a schmove, she's around.
Don't let your spaghetti boil over, Chris. I'll prove it for you.
How you gonna prove?
I'll show you.
anyway, if you increase that speed enough, it would produce other interesting orbits. For instance, it might produce an elliptical orbit, which is what path D is showing. And it might even go fast enough that the ball could escape the planet's gravity and leave. Now, the interesting thing is that each of these trajectories is what's called a conic section. It's a type of shape. And the first two, A and B, where they come back down to Earth, we call them parabolas, and we've in fact calculated some of those before. That was with kinematics. Maybe the most perfect shape might be a circle, where it goes all the way around the Earth and stays at the same height the whole time. That would be path C. As I mentioned, path D would be elliptical, which has other properties and goes out, and the altitude is changing a little bit, but eventually comes back to the same location. And then even the path where it escapes can be modeled with a conic section called a hyperbola. In high school, we'll focus on orbits that are circular paths, even though in reality most paths are elliptical. So, let's begin by talking about the velocity that might be required to produce this circular orbit around the planet. And for now, we'll keep things very general. We'll say just around a planet of mass m. To answer a question like this, we need to think about forces. What are the forces involved? Well, the force that pulls the object back down, that's changing its path, that's creating a centripetal force, if you will, is the force of gravity between the planet and the object in orbit. If the object is moving in a complete circle, then we can say that this gravitational force is exactly equal to the centripetal force required to create circular motion, and so that's a good starting point for an equation. So let's begin by saying that the centripetal force required is completely and perfectly supplied by the gravitational force. And we can make a few substitutions. The centripetal force formula is the mass of the object moving times the velocity squared divided by the orbital radius, which I'm going to use a capital R for so that you don't get it confused with perhaps the radius of the object itself. And then the formula for gravity is the mass of the object that's moving times the strength of the gravitational field at that point, which is g. On the surface of the Earth, this is 9.8. But in general, g depends on two things. It depends on the mass of the planet and how far away from the center of the planet you are. The higher up you are, that is, the greater your radius, the smaller g should be. In general, to calculate the gravitational field strength at any given location, we need to use Newton's law of universal gravity, and that is that the weight experienced at any given point is equal to a capital G. That's the gravitational constant, which is 6.67 times 10 to the negative 11th, times the mass of the object, times the mass of the planet, which I abbreviate with a capital M because that's usually much bigger than lowercase m, and divided by the radius squared. If we divide both sides of these by the mass of the object itself, we see that the mass of the object is insignificant and can be canceled out, and we get a formula for g, which is equal to the gravitational constant times the mass of the planet divided by the radius of the planet, or really the orbital radius, squared. So, making a substitution, I've got still mv squared over r is equal to m, and instead of g, I'll put in a capital G, a capital M for the mass of the planet, divided by the radius of the planet squared, and we have a proportion. Ultimately, we were asked to find the velocity, and so we'll try to get v by itself. We can cross multiply, and we get that mv squared times the radius squared is equal to m capital G, capital M, capital R. And to try to get v squared by itself, I'll divide both sides by mr squared. And the m's cancel, the r squareds cancel, the m's cancel on this side. R divided by r squared is the same thing as just an r in the denominator. And we have v squared equals capital G, capital M over capital R. And in general, if we take the square root of both sides, we get the formula that the velocity required for an object in orbit is equal to the square root of the gravitational constant times the mass of the planet times the orbital radius, which at a minimum would be the radius of the planet, but is often a little bit higher than that. So that formula can be used to calculate all sorts of different things, and in a second we'll calculate how fast one of those satellites above us is moving. So let's now use that formula to calculate how fast a satellite orbits around the Earth. Let's start by looking at a satellite that is orbiting at a height of 80 kilometers above the surface of the Earth. To give you some idea of the scale, if the Earth was that blue circle, another additional 80 kilometers, though it sounds really high, it's pictured by that red orbit around the Earth. So let's get calculating. The velocity of an orbiting object is equal to the square root of the gravitational constant times the mass of the planet divided by the orbital radius. In this case, the orbital radius is equal to the radius of the Earth plus the height of the satellite above the Earth, which I'll call h. The height above the planet is 80 kilometers, but the radius of the Earth is something we'll have to look up. Looks like the radius of the Earth is 6,378 kilometers. Notice also the mass of the Earth. We'll need that in a little bit. So that's 6,378 kilometers plus 80 kilometers for a grand total of 6,458 kilometers. One of the biggest difficulties in this orbital chapter is that this formula, because it has the gravitational constant in it, these numbers that we plug in always have to be in standard metric units. kilometers is not the standard metric unit, meters is. So a kilometer is just 1,000 meters, so it's simple enough to add 3 zeros to the end of this. 6,458,000 meters is the orbital radius. And the mass of the planet was 5.97 times 10 to the 24th kilograms. A kilogram is the standard unit for mass, so we don't need to convert that number. And then the gravitational constant is 6.67 times 10 to the negative 11th. And I honestly don't remember all the units for it. It does have some. And let me show you how I make these calculations. I usually take advantage of the calculator's storage capabilities. Whenever I make a calculation, one of the first things I'll do is find these relevant numbers and then store them as variables in our calculator. So for the radius, I'll type in 6,458,000 and then store that into the variable r. So alpha r. Then I'll do the same thing with the mass. 5.97 times 10 raised to the 24th power, and I'll store that into the letter m, so alpha m. And I might already have g stored in here. Let's see, if I just look alpha g, I've already got that one. And so to make my calculation then, instead of using the numbers, I'll simply type the formula, and that is the square root of capital G, or alpha G, alpha M, and then divided by alpha R. And this gives me an answer of about 7,800 and the standard unit for that is meters per second. And so you could quickly convert that into miles per hour if you want by dividing by 2. It's roughly going 4,000 miles per hour. That's how fast a satellite at that particular height moves around the Earth. Now, when you're discussing orbits, specifically orbits of satellites, it's very common to talk about the period. The period is the time that it takes to complete one full orbit. And the symbol we usually use for that is a T, specifically a capital T, to distinguish it from a lowercase time, which just means any amount of time. And of course the standard unit for that would be in seconds, although usually with orbits, periods are so big that seconds isn't very practical to talk about. We usually talk about periods in terms of minutes or hours or even days. And for some planets around the sun, we even talk about it in terms of years. So, in general, a formula for the period is simply the complete orbit, or the circumference, which is 2 pi r, divided by the velocity. And another version of that formula is that the speed that you're traveling is equal to 2 pi r, the full circumference, divided by the period. So, what is the period of that satellite that we just calculated? Let's look back at what its velocity was. We got 7,852 meters per second. And we're interested in the period. So the period is equal to the total distance, so 2 pi times the orbital radius divided by the velocity. And we can immediately calculate that if we go back to our calculator. Let's take that last answer, which is the velocity, and store it into the letter V. And now we can calculate what the period is by doing 2 times pi times the radius, so alpha r, and then dividing by alpha V. And we get what looks like a really big number, 5,167, but remember that is in seconds. So 5167 seconds. If we divide that by 60 seconds, we get a period of about 86 minutes, which is pretty standard for objects in what we call low Earth orbit. The space station is another object at relatively the same height. It orbits around in about 88 minutes. And so if you see it one night, chances are you might be able to catch it again 88 minutes later. I think that's pretty incredible to be able to think that if you were on the space station, you could watch the entire Earth rotate underneath you once in just over an hour. So, thanks for watching. I encourage you to come back again for our next video, which will continue this discussion about orbits, and specifically some observations that Kepler and his friend Tycho Brahe made in about the 1600s